This is the second lecture of Module 6. In this lecture, we will discuss the basic characteristics, performance characteristics of salient pole and non-salient pole type synchronous motors. First of all, we will discuss the case of a cylindrical rotor wound field motor. This is nothing but a non-salient pole type synchronous motor. Let us consider the simplified per phase sequence circuit of a cylindrical rotor motor. Here we can see that V is the stator input voltage, Is is the stator current, Xs is the synchronous reactance, and E is the excitation voltage. Now let's write the equation for power input to the motor. So power input to the motor Pin is equal to 3 VIS cos phi. Since this is a per phase sequence circuit, in order to find the power input to the actual power input to the motor, we have to multiply it with 3. So 3 VIS cos phi, where cos phi is the angle between V and IS, supply voltage and stator current. So if you have the expression for Is cos phi, we can write the expression for Pin. Before that, let's make an assumption that the stator losses are neglected. So neglecting stator losses, the mechanical power developed is equal to 3 VIS cos phi. That means input power will be equal to mechanical power developed if stator losses are neglected. So PM is equal to 3 VIS cos phi. Now let's find or obtain the expression for Is cos phi. Let's consider the circuit diagram, simplified circuit diagram. From that we can write the expression for Is. Is is equal to V angle 0 degree minus E angle minus delta all divided by J xs. Again it's equal to V angle 0 degree minus E angle minus delta all divided by J xs means xs angle pi by 2. Now we can write the expression for Is as V by xs angle 0 minus pi by 2 is minus pi by 2 minus E divided by xs angle minus of pi by 2 plus delta. Now the expression for Is cos phi. This is the expression for Is. So Is cos phi is equal to, we have to find a component of Is, one of the components of Is. So V by xs cos pi by 2 minus E by xs cos pi by 2 plus delta is equal to, this component becomes 0 because cos pi by 2 is equal to 0. So only this component will be there. Here cos pi by 2 plus delta becomes minus of sin delta. So minus of sin delta will give you plus sin delta. That is equal to E by xs sin delta. This is the final expression for Is cos phi. Now we can write the expression for power, mechanical power developed is equal to PM is equal to 3 VIS cos phi is equal to 3 V and into the expression for Is cos phi, that is E by xs sin delta. Now we can write the expression for torque. For that purpose we have to know the speed of the motor. Since this is a synchronous motor, its speed with the rotor will be running at the synchronous speed. So the synchronous speed of rotating field produced by stator, its omega ms is equal to 4 pi f by p radians per second. This is in radians per second. So the torque developed is equal to P by omega ms. It is equal to the expression for power 3VE by XS sine delta. This is divided by omega ms. So 3VE by omega ms into XS sine delta. This is the expression for torque developed. Now we can see that the power developed as well as the torque developed all are proportional to the, proportional to sine delta. So for a given field current, the value of E will be constant because E is the excitation voltage, and excitation voltage for a given value field current, the excitation voltage will be constant. That means the torque and power, as we already said, T and Pm are proportional to sine delta. The angle delta is called the power angle or torque angle. Next, we will discuss the torque speed characteristics of the synchronous motor with fixed frequency supply. Here the frequency is kept fixed. Then how the motor operates in motoring as well as braking mode, that we will discuss. Here the main things to be noted are Tmax is the maximum torque developed by the motor in the motoring mode, and minus Tmax is the maximum torque developed by the motor in braking mode, that is regenerative braking, second quadrant, and omega ms is the synchronous speed. So this straight line is the torque speed characteristics, this for motoring and this for braking. And pull out torque, this is the pull out torque or maximum torque above which the machine will go out of synchronism and may draw large amount of current, and it may cause damage to the machine. So in order to prevent the machine going out of synchronism, we have to provide extra protective devices such as circuit breakers to disconnect the motor from power supply when it goes out of synchronism or when it reaches pull out torque. Now let's see the different modes of operations. First, during motoring, what happens? During motoring, delta is positive. So when delta is positive, this term will be positive. That means torque will be positive. That means the operation will be in the first quadrant and E lags behind V. That we will discuss later. Then second case, during regenerative braking, that is in the second quadrant, delta will be negative. That is, delta will be negative means sine delta will be negative. So torque will be negative. So it will be in the second quadrant. So E leads V. And one more thing, the maximum torque, that is pull out torque, we discussed earlier, is reached when delta is plus or minus 90 degree. That means when delta reaches plus or minus 90 degree, this expression will reach its positive maximum or negative maximum. At this torque, the machine will go out of synchronism. Some other points to be noted are the power factor of a wound field motor can be controlled by varying the field current or E. That is an important feature of this motor. When the field excitation is small, the machine operates with a lagging power factor. That means when the value of E is small, the machine will be having lagging power factor. So if you have to improve the power factor, then we have to increase the field excitation. That means the power factor can be made unity or leading by increasing the field excitation, or the value of V is to be increased. These are the three cases of power factors. This is for lagging power factor. Here, the value of E will be less. Here, this is the unity power factor. E has increased. This is the leading power factor. The value of E has increased further. So, in lagging power factor, you can see that the current Is lags behind voltage by an angle phi. In this case, Is and V are in phase, so unity power factor. Here, the current Is leads the voltage V by an angle phi, so leading power factor. Next, we'll discuss the case of a salient pole wound field motor. That is simply salient pole salient pole type synchronous motor. Due to different synchronous reactances, that is direct axis synchronous reactance and quadrature axis synchronous reactance, the machine cannot be described by a simple equivalent circuit as we have done in the previous case. Here we can't draw a simple equivalent circuit. So we start our analysis from a phasor diagram. First of all, let's write the expressions for the current, the components of stator currents. Is is the stator current. ISQ and ISD are the two components of stator currents along quadrature axis and direct axis. So ISD, this is ISD. In order to write the expression for ISD, we will write the equation for ISD XSD. This length, this voltage or voltage drop is known as ISD XSD. So ISD XSD is equal to the component of voltage V along quadrature axis. So V cos delta. V cos delta. This length is V cos delta minus this length E. So V cos delta minus E will give you ISD XSD. So ISD XSD is equal to V cos delta minus E. So we obtain the expression for ISD. Similarly, we can write the expression for ISQ also. ISQ is equal to V sin delta divided by XSQ. From the expression for ISQ XSQ, we will get the expression for ISQ. So we have the two currents ISD and ISQ. Now we have to write the expression for IS cos phi in order to write the expression for the power. So IS cos phi is equal to ISQ cos delta minus ISD sin delta. Substituting the values of ISQ and ISD as obtained earlier, we will get the final expression like this. IS cos phi. Now, we will write the expression for power PM. PM is equal to V3 VIS cos phi. It is equal to PM is equal to 3 into V into the expression for IS cos phi. Similarly, for torque, T equal to Pm by omega ms, it is equal to 1 by omega ms into the expression for Pm. So, we have obtained the expressions for power and torque. The torque speed characteristics will be the same as that of a non-salient pole type synchronous motor. So that's not discussed again in this lecture. In the next lecture, we will discuss the variable frequency control of synchronous motor. Thank you.